Hello, everyone. My name is Shailesh. I'm a master's student at the University of Tennessee at Chattanooga. I want to thank my supervisor and the director of Connect Smart, Dr. Wahid Tasfani. Today, I'm presenting on distributed dynamic algorithm based on ADMM to solve the economic dispatch problem in power system. So here's the outline. First, I introduce with some background and motivation, followed by some mathematical background on ADMM and consensus algorithm. Then I talk about ADMM on different architectures, then some case study and conclusion. So in the introductions, let's start with some background. The 21st century electric power grid will no longer be what it has been for last century because of the proliferation of distributed energy resource driven mainly by the environmental concerns. When we say power system, the immediate picture we have is a bulk power system with large generating units, high voltage transmission, and low voltage distribution side. Today's power system is moving to small scale with the variable energy resource participating at the edge of the grid. When the classification of the physical layers of the power system itself is to be revisited, obviously this is the time to think of new ways to control, monitor, and optimize the resource. And economic dispatch is a typical resource allocation problem. Before I dive into economic dispatch problem in particular, here is the overview on the architecture of different algorithms: centralized, decentralized, and distributed. In a centralized, a central entity collects all the required data and runs the optimization. In decentralized, each agent does its own optimization, but it needs a coordinator. Our coordinators, often called master node, that tightly coordinate with all the agents of the market in order to clear it. In distributed, a master node is no longer needed. Each agent optimizes its resource based on its own and its directly connected neighbors. So the computation is now divided among agents, and so does the communication. ADMM has been extensively reported in literature for resource allocation problems. This paper solves dynamic economic dispatch to schedule DER with the need of a central coordinator, the point of common coupling. This is by definition decentralized. The second one exploits average consensus to implement a distributed form of ADMM, but it has a strong assumption that the demand of the network should be constant. When we can call it distributed, but again, there should be some form of coordination to let all agents know the demand of the network. Now let's talk about some mathematical background on ADMM and consensus algorithm. What is ADMM in general? So if this is an optimization problem, a constraint optimization problem, then this is the Lagrange relaxation of that constraint optimization problem. The lambda is the dual variable associated with the equality constraint, and that's what the market price is. So in order to improve the convergence speed of the problem, the extra penalty term is added, and this is now called the augmented Lagrangian. But the convergence speed comes at a cost of sacrificing the decomposability property of the problem. So here is where comes the ADMM that has both the decomposability and the superior convergence speed. So here is a dual updater that gathers the residual contributions of equality constraint, updates its dual variables, and broadcasts back the information to all agents. So all the agents can now solve their optimization problem themselves. In consensus, so if you think electric grid as a connected graph, like in the figure, then any node can estimate the average of the network based on the information of its neighbors. So that's what distributed means. For example, node 1 has the information of node 2 and node 3, and it can estimate the average of the entire network. Similarly, node 3 can look into node 4 and node 1, and it can estimate the average of the entire network. So all the nodes can do the same. Obviously, each node has a different estimate on the average, but the average is one value. If A is chosen carefully after subsequent iteration, their estimate of average reaches to one consensus value, and that consensus is the average. So the choice of matrix A determines the stability and conversion speed. We have some assumptions like the matrix should be W stochastic and the graph should be connected. So now what if the average of the network itself is changing, or in other words, the value at the nodes are changing with time? So for that, we have dynamic average consensus that tracks the change with time. Now let's talk about ADMM-based distributed economic dispatch. So this is economic dispatch, a typical resource allocation problem in power system. This is the objective function and the global network power balance with generator constraints. What we see in the picture is a centralized economic dispatch, a control room that has the data of all the generating units, and it runs the optimization and broadcast back the schedule to all the plans. As obvious, the control room controls all the decisions of generating unit, and each unit has to share all its control variables. With the proliferation of DER and the volume of data that we have to now collect to run the optimization, it is not practical for a central entity to do so, not computationally, not in communication-wise, and even for data privacy. So here is the mathematical formulation of economic dispatch. Here we see the global constraint that requires the power balance. When we see this problem, this problem is inherently decentralized. So any decentralized algorithms will be able to solve it. So this is the ADMM implementation of economic dispatch as it is. We see the dual updater that adjusts the dual variable to clear the market, which is to ensure power balance of the network. Here we see each agent needs demand and generation of all agents, that is two modes of communication. So we introduce a new variable called average power mismatch and do some algebraic calculation. So now this problem modifies to this problem, this problem, and here we have the average mismatch of power of the entire network. And remember, this is now again still a global variable. So for this optimization problem, we have PZD, W, and N as a global variable. So if we have a dual updater, then to interpret in the language of optimization, the dual variable W here is constantly pulling the decision variable towards the optimum value. Now we are interested in a distributed paradigm. So for that, we should find a way to localize these three global variables. So to localize those global variables, we have this dynamic power mismatch consensus algorithm and dual variable consensus algorithm. So with the consensus algorithm like I presented before, now each agent can estimate the average mismatch of the whole network based on the information of its neighbors, and this is the dynamic part. So this is the dynamic average consensus, and this one is each agent can estimate the dual variable with the using average consensus and adjust this dual variable to clear the market. So now the problem changes from a decentralized setting to a distributed setting. You see these two variables were global here, and here it's localized. So it now no longer needs that dual updater. So for a common cost function, if we differentiate this, and then we get PGI k plus 1 at this value. So this is now a completely distributed form of ADMM. So here is distributed economic dispatch. This is the architecture that's implemented. Here is the different plant. This is solar, the other plant, and now this plant has the information of this solar, and this plant and this plant. For this solar, it just has the information of this one, and each agent now solves the optimization problem on their own without a need of master node or a central entity. This is the algorithm we wrote for a MATLAB. We see PGI, then some update process, and lambda is some scale form of the dual variable. These values are communicated back to its directly connected neighbors, and each agent updates its decision variable. Now the case study, for case study, we have this IEEE 30 bus network with 6 generating units and IEEE 300 bus network with 69 generating units. So we have two assumptions. Every bus is a single agent. When we say agent, we say it's a bus, and the communication network is assumed similar to electrical network. So for 30 bus, this is the communication network. So here is the simulation result. The demand changes in every 20,000 iterations, and it's carried for 100,000 iterations, and the entire process takes just 1.94 seconds. So here is the consensus on the market price. So what we see here is each agent has a different lambda before, and they have finally find consensus to one value. And when there is a subsequent change in the demand, then again, each agent adjusts their lambda to, and all those lambda go into consensus. Similar with the market price, this is the dynamic average consensus of power mismatch. For the power mismatch, each has a different estimate, but those all estimate goes to zero. So this shows that with a localized estimate, the network's power balance is ensured, and these all are happening in microsecond and millisecond. So here what we see is the generation is following the demand. Once the residuals are zero, then the network's power balance is ensured. This is the case of the primal and dual to be the saddle point of the Lagrangian function. So when these conditions are met, all the generators are at their optimum point, or we say the decision variables are at the optimum point. So here is the result for 300 bus, the same simulation setup. We have the power mismatch, different power mismatch, but they finally go to zero. And similar with the market price, they have different market price, and they finally settle to one market price, and the market is clear. Obviously, with the larger network, it takes a little while. So the entire simulation setup took just 7.12 seconds, and but still these iterations are carried in a millisecond. So similarly, once the residual go to zero, the power balance is ensured, and these are for all 69 generating unit, the generator at their optimum decision points. Now the conclusion, so we proposed a novel distributed ADMM algorithm and applied that in a power system economic dispatch problem. So that economic dispatch is a real-time economic dispatch. That's why we call it dynamic. So we test in 30 bus and 300 bus, and the optimum solutions are achieved in less than 10 seconds for 30 bus. For 300 bus, the convergence is little slower than the 30 bus because of the size of the network, but still it is achieved in less than a second. And thank you.